Institute of Engineering and Technology.
We already gone through limit for function of one variable and continuity for function of one variable. Today in this discussion we are going to cover function of multi-variables, in particular function of two variables. We'll see how to approach the point on the surface, we'll see how to define the limit mathematically, we'll also see how to define continuity for function of two variables. So let us start this thing. The first part of our discussion is how to define function of two variables graphically. So this is nothing but the graphical interpretation of function of two variables. Here I am considering the first part as function f of xy equal to x square plus y square. We'll see how to draw the graph from 2D to 3D. So two-dimensional xy plane is reserved for input, and then I'll take rule x square plus y square to generate the third dimension, which is z equal to x square plus y square. So in this case, what we'll do, if I take input from the blue circles on the xy plane, the corresponding outputs will be on the pink circle on the surface. Now these blue circles are known as the contour lines, as well as the pink circles are known as the level surface or the level curves on the surface. So for simplicity, if I take the points from the outermost circle in xy plane, the corresponding points are jumping on the pink circle on the surface. So this is how inputs are taking place from xy plane to z dimension. In similar way, you can see here on all different circles, the points are jumping from xy plane to surface. So if we consider the same structure for all different inputs in the circle, ultimately it will give me a surface. So this is how the construction of function of two variable is done. Now we'll see, remaining on the surface, how we can approach towards a point on the surface, and for that reason I am considering this function x square plus y square, and I will fix the point of approach as origin. Now in this case, let us consider this construction for moving towards a point. Now throughout this discussion, I am considering surface, which is x square plus y square, and I will focus on point origin, which is input. So this is the point of discussion, origin. Now what I want to do, I want to construct different possible paths to reach this point from the domain, and for that reason, suppose I fix the first dimension as x-axis. So now my inputs are coming from x-axis, and correspondingly my points are moving on surface like this. This is how you can move towards origin, by considering all inputs from x-axis. In similar way, we can consider another dimension also. So for that, I am considering y-axis as input for these points on the surface. So now I am approaching towards origin by taking inputs from y-axis. You can see clearly from this graph that points are with input from y-axis. Now these are two fundamental dimensions. We can construct a random direction which is y equal to x for input. So if I take y equal to x, then my inputs are coming from line y equal to x, and correspondingly my points are moving on surface, something like this. In similar way, now you can think that there will exist many more directions from which we can consider input from xy plane. But for simplicity, let us consider one more dimension which is actually useful, and that is y equal to minus x. So if I take input from y equal to minus x, this is how my points are moving towards origin, remaining on the surface. So the natural question would be, how many such directions are possible? If we figure out, or if we rotate this parabola on x square plus y square, we can see clearly there are infinitely many directions to reach this point. Now with every direction there exists a black line which in future is known as tangent. So if I construct all these black lines, it will give me a plane, and that plane will consist of all such tangent lines for the point. Now this plane contains actually all possible paths for approach towards origin. We can see clearly that this plane is existing with all different points on the surface. So this is how you can construct the idea and generalize it. So here I am generalizing the idea of approach towards a point on the surface. You can see clearly here the point is now randomly taken on the surface, and correspondingly the plane represents infinitely many such directions to reach the point remaining on the surface. So this is whole idea of moving towards a point or approaching the point in surface. Here we are considering x square plus y square and point origin. Now from this we can define limit for function of two variables. So the first part for the definition of limit for function of two variables is how to define mathematically various paths for the limit. So for that I am considering function e raised to minus x square plus y square plus 1. So this is my input. If I take point of approach 0, 0, and if I construct a neighborhood in surrounding of this point, here I am representing it by a cylinder which is actually a circle in xy plane. This is nothing but the neighborhood of point 0, 0. So now I am focusing on this neighborhood only, and then I want to construct all possible paths in such a way that they are mathematically well defined. So if I go for the top view of this particular structure, then I can see clearly that the point of interest is origin, and correspondingly my surrounding is given by this blue circle. So now I am representing origin by yellow point and surrounding by blue circle. So if I select a random point which is represented by purple dot in this ring, which is neighborhood of point 0, 0, then now I want to discuss how to construct all possible mathematical paths to reach point 0, 0 from point xy. So the first obvious path will be moving parallel to x axis and then moving parallel to y axis. So we can see clearly this is how we are moving on a boundary of the rectangle in which these 2 points are on the diagonal, xy and origin. So this will give me my first path of approach, which is x tending to 0 and y tending to 0. Now in similar way we can go through the next part, or we can say the another boundary on which my point will float first of all parallel to y axis. It will reach point x0 and then it will move towards point 0, 0. So this is how we can see a point is moving from x0 to origin. So this is my second path, in which first of all I will take y tending to 0 and then I will take x tending to 0. Now clearly the shortest possible path is moving towards origin by a straight line. So for simplicity I am assuming a straight line which is given by y equal to mx, and the first transition will be somewhere in the neighborhood, and finally remaining in that neighborhood we can construct another part of this path. So the first part of this path is limit y tending to mx and then limit x tending to 0. So this is nothing but my third path, y tending to mx and x tending to 0. Now we can take a curved paths. So this is how we can move parabolically from xy to 0, 0. Means I am remaining on the parabola and I am moving towards origin. So this is how we can add curvature to the graph. We can also take a random path which is given like this, but it is mathematically well defined. So if I want to move from xy to origin on this path, it is also another possibility. So these are all different possibilities to construct mathematically well-defined paths from xy to origin, which are actually with curvature. So in first case I am taking y tending to x square, and then in the neighborhood I will take x tending to 0. Second path is y tending to mx raised to n. This is generalization of all curved path. So in general, this fourth path y tending to mx raised to n and x tending to 0, it consists of infinitely many such curved paths. So now we are moving towards a meaningful way to construct the definition of function of two variables, and which is limit for function of two variables. So the first case is limit is existing. Now let us check first of all or verify our construction in which cases limit will be existing and in which case limit will not exist. So this is the first case where limit is existing. I am considering a saddle surface e raised to y square minus x square. Again, my point of interest is origin. I am constructing neighborhood around this point, and slowly I will consider the top view and I am moving towards the paths which we defined already in our previous discussion. So here I am tending to 0 and y tending to 0. So this is how first of all I will take x tending to 0 and then y tending to 0 on this graph. So you can see clearly over here the input is given by f of 0 to 0, 5, which is 1.23. So that means we are moving parallel to x axis. So now we are jumping towards origin on the first path. So at the end of the journey, our first path will give result f of 0, 0 equal to 1. Now let us consider second path, y tending to 0 and x tending to 0 later on. So here I will take first of all y tending to 0 and then I will take x tending to 0. So let us consider the same thing on the graph. We can see clearly that the value of f of 0.50 is 0.77, so in which we are moving first of all parallel to y-axis, and now we are moving parallel to x-axis. Okay, so again function's value is same. Now I am taking third path, which is y tending to mx and x tending to 0. That means I am moving on a straight line like this. So this is how your point will move. So if I start moving towards origin using this idea, again I will be somewhere in the neighborhood, and finally whenever I will take x tending to 0, it will give me final answer. So the last possible path is curved path. So suppose I take a parabolic journey like this, or I take a random mathematically well defined path like this. So initially it will move on parabola, and finally whenever it will reach the point, it will give me value 1. So this is how on all various mathematically well defined paths my value of limit is same. So in some sense we can say that limit will be existing, but still we need to verify it with epsilon delta neighborhood, which we are going to define after this second case. So this is the case where I want to construct the definition of epsilon delta neighborhood. This is graphical construction. Algebraical construction will be at last. So here I am considering epsilon and delta definition. So this is nothing but the deleted delta neighborhood of origin, and if I shrink the radius of this, ultimately you can see it is converging at a single point which is defined by L. So this is nothing but epsilon neighborhood of f of 0, 0. This is how the limit is existing for function of two variables. Now let us consider the case where limit is not existing. If I consider this type of surface, if I take a surface flat plane and if I pinch it at some particular point, the pinch is actually at point 0, 0. You can see clearly if I fix the direction y equal to x to approach point origin, my values are something given by 0.499. We can see clearly here, and this gives me that limit is equal to 0.5 if I fix the path of approach by y equal to x. But now what will happen if I take another path which is y equal to minus x? If I approach origin using this path, then you can see clearly here the value at neighborhood of origin on this path is minus 0.5. It clearly says that my function is changing the value whenever I will start approaching towards origin. If I move on line y equal to x, it gives me 0.5. If I move on line y equal to minus x, it gives me minus 0.5. That means we identified two paths on which the value of limit is differing. And so we can say limit does not exist. So now, what is definition of limit? From this we can construct the definition of limit like this, that if for every epsilon greater than 0 there exists delta greater than 0 such that whenever we are taking points from the deleted delta neighborhood of point AB, then corresponding points are transformed into the epsilon neighborhood of function at point 0, 0. In such case we can say that limit for function f of xy is equal to L whenever xy is approaching point AB. This is the definition of limit for function of two variables. Now after this we can define definition of continuity for function of two variables also, which is almost parallel to continuity for function of one variable. The only change is here the definition of limit is generalized. So in function of one variable we defined limit using only two paths. Here we are defining limit using infinitely many paths. So the first condition is as usual that f of xy must be well defined at the point AB. Second condition is limit at point AB must be existing, which is equal to L, and the third condition is both of the previous conditions must be same. So this is how we are defining function of two variables in case of limit and in case of continuity. In future we will also see how to define derivative for function of two variable, which is known as partial derivative, and we'll start from the derivative for function of one variable. Thank you.
LJ Institute of Engineering and Technology.